Lorentz model is one of the most common for describing interaction of light with matter. It is based on interaction of two charges, where the electric field works as a driving force and electromagnetic attraction as restoring force. The induced displacement dipole radiates and finally composes the total field. The details of the derivation can be found from many basic optics books, and they are not described here. Permittivity or relative permittivity according to the Lorentz model is given here. This model applies especially well for gases, in which case the constant is 1. For solid materials, we use the epsilon infinity instead. In this model, omega 0 is the characteristic resonance frequency between the oscillating charges. Epsilon infinity is the high frequency limit of permittivity. F is the oscillator strength of each of the resonances. Gamma is damping of the resonance. And finally, omega p is the so-called plasma resonance frequency, which is a natural frequency of density oscillations of free electrons. This plasma frequency plays especially a significant role in metals and highly doped semiconductors, as well as plasmas. Here we see an example of how the permittivity and refractive index look like as a function of optical frequency. At resonance omega 0, we observe rapid change of both real and imaginary parts of the permittivity. The loss, denoted by the red curve, is highest exactly at the resonance, and far away from the resonance, the permittivity tends to the high frequency limit. The corresponding refractive index is the square root of the relative permittivity. Its shape is very similar, as you can observe. If we think about solid materials, we know that their atomic resonances often takes place at the ultraviolet wavelength range. Therefore, as a crude rule of thumb, the refractive index is increasing towards the ultraviolet range, and its loss is increasing simultaneously. A direct simplification for dielectrics with negligible loss is given by Selmayr model. This is essentially a Lorentz model when the damping term gamma is removed. This equation describes materials very well, but it's not physical since it neglects loss near the resonance. In general, refractive index and loss depend on each other through the so-called Kramer's chronic relations. There are several other models of refractive index which we shall take a look next.